Hey everyone, today we're going to start learning about all the applications of everything we've been learning with exponential functions. So basically what I did was I took all the word problems from what we've been talking about and grouped them all at the end here. But before we get into that, we're going to start with a little would you rather question. So here are your options. Option 1, you can get $100 today and an additional $200 each day for a year. Option 2, you get 1 cent today and you can double your money each day for a year. Which option would you rather take? Go ahead and take a minute and decide which one you want and highlight your choice. In order to figure out which one of these equations, which option is better, an equation would be helpful. So let's think about the two types of functions that we've learned so far this year. Those two types. Think of them in your head. They are linear and exponential. So which one's which? Hopefully you were able to come up with the fact that option 1 is a linear, while option 2 is exponential. Anytime you are adding the same amount every day or every year or every so often, you are talking about a linear function. However, every time you are multiplying by the same amount every day, every year, or whatever it is, that's an exponential function. This case, we're doubling. We know that's the same as multiply by 2. In order to come up with our linear and exponential function or equation, it would be helpful to think of our options for those formulas. So think back to the first semester, we talked about linear with 3 different formulas. Our options for a linear equation include point-slope form, slope-intercept form, and standard form. Those formulas, hopefully you can remember them and fill them in on your own. As a reminder, point slope is y minus y1 equals m times the quantity x minus x1. Slope intercept is y equals mx plus b. And standard is ax plus by equals c. Each one is helpful in a different scenario, but for this scenario, we would be best to represent it with slope-intercept form. In slope-intercept form, you have to fill in the slope and the intercept. So on this problem, we have 2 numbers here. You get $100 today and an additional $200 each day. The slope is the 200 because that's how much you get each day. However, the intercept is what you start with. That is what you're getting today, $100. So our formula would be y equals 200x plus 100. Similarly, for exponential, we know the formula that we've been learning is y equals ab to the power of x. This might be a little easier because there's only one formula to pick from. We know that A stands for the y-intercept. Just like with linear equations, the y-intercept is how much you start with. So how much are you starting with? How much do you have today? That's 1 cent. To write that as a dollar amount, that would be 0.01. So 0.01 is A, or the y-intercept, because that's what you start with. Then b, the base, is what you multiply by each time. So in this case, it's going to be 2 raised to the power of x. So in both formulas, you'll see that you have to know the starting amount, whether that's 100 in option 1 or 1 cent in option 2. the starting amount is always the y-intercept. Then you also have to know what you're adding or multiplying by each day or each time. In linear, it's the slope. In exponential, it's the base. So hopefully you're starting to see the similarities and differences here between linear and exponential. Now, in order to find out which option was the better option, it would probably be helpful to answer some questions. Maybe you can come up with this question on your own. The question that we need to be answering is, how much money maybe you can finish that question in your head. You know what I'm going to say. How much money do you have after 1 year? In order to answer that question, it's going to be helpful to know what x and y stand for in these equations. See if you can figure that out. Remember, x is our independent variable, which is usually time. In this case, it's the number of days. And y is the dependent variable. In this case, it is our amount of money. So to answer this question, how much money do you have after 1 year? Are you looking for x or are you looking for y? You're looking for y. If you're looking for y, you have to know x. So the number of days, if it's 1 year, that's going to be 365. So now whichever option you chose, go ahead and figure out how much money you have. Plug in 365 for x. So we'll do 200 times 365 plus 100. Or you're going to go y equals 0.01 times 2 raised to the 365 power. You can use your calculators or whatever you need to figure these out. If you picked the linear function, you plug that into your calculator, you should get 73,100, meaning that after a year, you have $73,100. That's great. You have a lot of money. It's a lot. You could pay for college with that money. Now let's see how much you would have if you had chosen option 2. For those of you that chose option 2, let's see what happens when we plug that into our calculators. When we plug that in, we have 0.01 times 2 raised to this 365 power, and we press enter, and it gives us this error. So let's go ahead and read that error. It says overflow, and read the rest of it. It says calculation exceeds the range of values this machine is able to display. So what do you think that means? Basically, what that means is you have so much money that your calculator can't even show you how much money you have. So you are super rich, and we need a different way to figure out how much money you have. Your calculator can't even show you that many numbers at once. So maybe you would want to try Googling it and figure that out. When you type that into Google, it gives us 7.5, that long decimal, e plus 107. We've seen e on our calculator before in this chapter. Let's remind ourselves what that stands for. So let's write it down, 7.5 e plus 107. Let's see how much money do we actually have. We know we're super rich. On your calculator, that e, it shows up as a capital letter. It might say E107. That means the same thing. But we talked about when you see that on your calculator, what it means is times 10 to that power. So it's saying times 10 to the 107th power. That's scientific notation right there. So what this is saying is you have 7, 5, and you have 106 zeros after that. So I'm obviously not going to write those out. That's saying there are an extra 106 zeros after that 5 because you move your decimal place over 107 spaces. So you have a ton of money. How did that happen? How in the world could you get that much money? Let's look at our graphs. Maybe that can help us to wrap our head around this. With a linear function, we know that the graph makes a straight line. So although you are starting out with a lot more money, you're starting out with $100, meaning your y-intercept is 100. You're only going to be going up at a constant rate. It's a straight line. You get an extra $200 a day. Linear is always represented by a straight line. However, for exponential, we remember that curve that we get in our graph. So although we're only starting out with a penny, way less money, almost zero, this is going to be exponential growth. So our graph is going to be going up like this. We get this nice exponential curve. And notice how fast that starts to go up. So in the long run, exponential is always going to go up higher than linear. Maybe you could ask yourself, when will the exponential get you more than the linear? That's something you could figure out. Let's talk about, make sure we understand what these exponential equations, how to write them, how they apply to the real world, and what every variable stands for. Hopefully you're starting to see kind of some similarities and differences between linear and exponential. But let's make sure we're all on the same page. So the key idea is that exponential functions, they're used in real life to represent exponential growth and exponential decay. So think back to that money activity we just did. The money kept doubling and doubling, which we said was an example of exponential growth. Anytime you have an amount increasing or decreasing by a percent, you can use an exponential function to represent that situation. In that money example, how much growth do you think there was? What percent of growth do you think that was if you're doubling? That would be a 100% growth. Remember the equation, it had 2 as the base. It wasn't perfectly y equals 2 to the power of x. It was the base of 2 though. How does that 100% growth relate to the base of 2? Let's figure that out. 100%. How do we write 100% as a decimal? It's equal to 1. Whenever you're changing a percent to a decimal, you divide by 100 or move the decimal place over by 2. So another example, 50%. What decimal do you think that would be? Divided by 100, it's 0.5. You'll also have to know how to change it the other way. If you have 0.3 as your decimal, what percent is that? You would multiply by 100, so move it 2 to the right, you get 30%. You have to be able to convert between percent and decimal. So how does that percent, 100% or 1 relate to the 2? Here's why. The formula is y equals a times 1 plus r to the power of x. So what we're doing is all we're changing is the base we're saying is equal to 1 plus the rate. The base is always equal to 1 plus the rate. So if you had a rate of 1 or 100%, 1 plus 1, that's how you get a base of 2. So all we're changing in our formula is we're saying the base is 1 plus the rate. Otherwise, it's staying the same. Y equals a b to the power of x. So as a reminder what all these variables stand for, y is our final amount. A is our initial or our starting amount. That's always the y-intercept. R is the rate. You always have to change the percent to a decimal. It's positive for growth and negative for decay. Finally, x or t, you might see people just use t there instead because it always is the time. The independent variable on these is always going to be time. Now let's take a look at an equation and see if we can figure out what the different parts of it mean. For this example, it's saying the number of users in millions that belong to a social networking site can be represented by this function. Y equals 1.5 times 1.4 raised to the power of t, where t is the number of years since 2013. Interpret the parameters of the equation. So basically what that's saying is it's asking you to explain what A and B mean. So in this context, explain what A and B mean. So first you have to be able to pick out the A and the B. The A in this case is 1.5. The B is 1.4. Remember, A is the starting amount. So you're going to look at where this started or when this started. It was 2013. So what this is saying is that in 2013, you want to be really specific about when it started. Give a specific year if possible. In 2013, there were 1.5 million users on this social media site. Remember, A always stands for the starting amount. Now you can use B to figure out the rate of growth or decay. So think back to what we learned. If the base is greater than 1, we know it's growth. If the base is between 0 and 1, it means it's decay. So before we even find the rate, we know this is going to be exponential growth because the base is greater than 1. In order to figure out the rate of growth, we use this 1 plus r equals the base. So if 1 plus r is the base, or 1.4, you should be able to solve that for the rate. You would subtract 1 from both sides, and you get the rate is 0.4. So what this is saying is that it, or the number of users, you want to be really specific about what we're talking about. The number of users grows. Anytime it's positive, it's growth. Anytime it's negative, it's decay for the rate. The number of users grows by, it's not 0.4 every year. We have to change that back to a percent. Multiply it by 100, you get 40%. So we'll say the number of users grows by 40% each year. If you need to make a note to yourself, we knew that that was growth because the base was greater than 1. And we also confirmed that because the rate was positive. Now you can go ahead and try the practice problem on your own. See if you can interpret the parameters of the next equation. All right, when you're finished, you can go ahead and check your answer here. And then we'll move on to example 5. This one says, during an economic recession, a charitable organization found that its donations dropped an exponential amount each year. They found that the equation y equals 390,000 times 0.989 raised to the power of t could represent their situation, where t was the number of years since the beginning of the recession. Interpret the parameters of the equation. So before we get into this, first let's make sure we all know what a recession is. That's when the stock market goes down, the amount of money that people are making is maybe not worth as much as it has been in the past. People are struggling economically to pay bills, stuff like that. Hopefully you learn about that in social studies class. So it would make sense that people aren't donating to charity as much and their donations are dropping. If we look at this equation, you might already notice the base b is less than 1 this time. Remember, if the base is less than 1, that means that it's exponential decay. If the donation amount is dropping, we know that's going to be decay. So let's go ahead and interpret the A value first. So what it's saying is that in the beginning of the recession or before the recession, they were receiving $390,000 each year. However, now the base is 0.989, so we're going to have to figure out the rate. We know 1 plus the rate equals the base, so 1 plus the rate equals 0.989. And to solve that for r, or get r by itself, we need to subtract 1 on both sides. And this time we know we're going to end up with a negative. You get negative 0.011. As a percent, you're going to multiply that by 100 or move the decimal place to the right by 2. So that would be negative 1.1%. So to interpret what that's saying is that in the beginning of the recession, they were receiving $390,000 each year, but now their donations are decreasing by 1.1% each year. You do not need to put the negative because you already said it's decreasing. So when you get a negative rate, you're not going to include that as part of your explanation. You're just going to use the word decreasing. Now go ahead and try the next problem. Okay, when you're ready, you can go ahead and check your answer. On this one, we got another negative rate. And whenever the rate is negative, you're going to notice the base is smaller than 1, which all goes with exponential decay. So to recap, if you have a positive rate or a base greater than 1, that's exponential growth. Whereas if you have a negative rate or a base between 0 and 1, less than 1, that is exponential decay. So far in this lesson, we have just been getting the equation and interpreting what it means. Next, we're going to start looking at getting information and coming up with the equations more on our own. So I look forward to talking to you guys then. We'll do more practice with this again in the next lesson. See ya. Bye.